So in this video, we will talk about the infamous potato problem. It's from the 2017 AP Calc AB exam. It appeared on the BC exam that year as well. And it is a non-calculator question that involves a potato. And so if you read the situation, at time 0, we've got a boiled potato. It's taken from a pot on the stove. It's left to cool in the kitchen. The internal temperature of the potato is 91 degrees Celsius when it's removed from the pot, and the internal temperature of the potato is greater than 27 degrees Celsius for all times that are positive. The internal temperature of the potato at time t minutes can be modeled by the function h, which satisfies the differential equation that we see here. H of t is measured in degrees Celsius, and at time 0, the temperature of the potato is 91 degrees. So in part A, they ask us to write an equation of the line tangent to the graph of function h at t is equal to 0. Use this equation to approximate the internal temperature of the potato at time t equals 3. And so if you think about what you normally need to do to piece together the equation of a tangent line, you need two things. You need the slope of the tangent line, you need the point of tangency. So we know the t value, the independent variable for the point of tangency's value is 0. Well, it's a tangent line to the graph of h, and corresponding to that input value of 0 for t, we have an h value of 91. So the point of tangency is 0, 91. What about the slope? And the slope is kind of weird because if you think about it, we are so used to being given the independent variable's value here. We toss that independent variable's value in place of the variable in the derivative and we get our answer. The thing we have to kind of pump the brakes with a little bit here is the fact that this is a t value of 0, and obviously I'm not going to put 0 in place of h. So I need to recognize that the h value that corresponds to the t value of 0 is 91. And so 91 goes in place of h in the derivative in order to help piece together the slope of that tangent line. And if you go ahead and do 91 minus 27, you get 64. Negative 1/4 times 64 gives you negative 16. You could have left your answer looking like this. I went ahead and simplified it a little bit though. Got negative 16 for the slope. What is the equation of that tangent line? Well, I want point slope form here, right? So y minus y1 equals m times x minus x1. That's actually kind of poor notation. I should probably have used a t right here rather than an x, only because that was the independent variable as specified within the problem. So if I had the chance to go back and touch this up, I'd probably change that to a t. But then it still is going to be able to produce the estimate that we want to attain here. What is our estimate for h of 3? Well, if we use the y value from the line to estimate the y value from the curve, all we're going to do is we're going to solve this equation for y, so just add the 91 to the other side, and we're going to use the y value at this independent variable value, so at that x value or at that t value. And so, this right here would receive full credit if you left it looking like I have right here on the AP exam. I went ahead and simplified it a little bit and got down to an approximate temperature of 43 degrees Celsius at time 3. In part B, they ask us to use the second derivative of h with respect to t to determine whether that estimate that we just made in part A is an underestimate or an overestimate for the actual internal temperature of the potato at time 3. So to find the second derivative, we have to be careful with this because we're doing the derivative with respect to t. And so the derivative on this side gives us our second derivative. The derivative on this side, I can copy that negative 1/4 into the derivative. And then the derivative of h minus 27 with respect to t is going to be dh dt. And what did dh dt equal? Well, dh dt is equal to what we have right here. So you'll see in place of the dh dt that's appearing right in this position, I've replaced it with what I just highlighted there. I went ahead and simplified it a little bit. I multiplied these two fractions together, got positive 1/16 times that quantity h minus 27. So if we are asked to use the second derivative to try and decide whether or not that estimate in part A is an underestimate or an overestimate, it seems to kind of hint that we're going to have to make some concavity arguments to build this argument. And so what I recognized here is that, h of t is greater than 27. They told us that up in the problem statement. And since h of t is greater than 27, this second derivative is always going to be positive, right? 1/16 is already positive, and then something bigger than 27 minus 27 is definitely positive. Positive times a positive makes that second derivative always positive. That means that h of t is always going to be concave up. Well, how does that allow us to decide whether or not we're dealing with an overestimate or an underestimate? Well, think about what we did in part A. We used the tangent line based at the ordered pair 0, 91. So here's the equation of that tangent line. We took the y value from that tangent line at 3, and that is not the y value. That should be a 43 there. That's my fault. I don't know if I'm going to be able to make this look as nice and I guess I have the wrong color there, but that should be 3, 43, right? Wasn't that the answer that we got back here? Yeah, my fault. I just wanted to make sure that that synced up with that answer from part A. So we've used this y value from the tangent line at the t of 3 to estimate the y value from the curve. Well, if the temperature of the potato is decreasing, but we've just proven that that curve is always concave up, that's going to indicate that the slope of the tangent line is increasing as we progress across the curve here, and that's going to push this tangent line to be below the y value on the curve at the t value of 3. Because of that, our estimate from part A is definitely going to be an underestimate, right? We wanted this value from the curve at time 3. We got a value that's a little bit below that because of the concavity of the graph. Then in part C, they talk about an alternate model for the internal temperature of the potato. It only holds for times that are smaller than 10, and it's going to satisfy this differential equation. So G of t is also measured in degrees Celsius. We have that same initial condition. At time 0, the temperature is 91. We're asked to find an expression for G of t. Based on this model, what is the internal temperature of the potato at time 3? So if you're asked to find this function G of t, you've got to solve this differential equation. And so if you separate your variables, I left the -1 on the right-hand side and multiplied the dt over to that side. And then I divided the dg by the quantity that was raised to the 2/3 power here. I realized if I was going to integrate each side, I do have an inner function within the quantity that's raised to the 2/3 power in that denominator, so I let u equal that. The nice thing is that du dg was 1, so I don't have any cancellation that has to happen. I don't pick up any new constant values from that substitution. I am putting u in place of g minus 27. And then I also realized I can bump that u to the 2/3 into the top of the fraction by changing it to a negative exponent on that u. And so I applied my power rule for antiderivatives, add 1 to that power, divide by the new power. Well, dividing by 1/3 is the same as multiplying by 3. I took my work up to the other side here. I guess I'm kind of forgetting what I did here. That should be pretty obvious though, right? Antiderivative of -1 with respect to t is negative t. That is the side with the independent variable on it, so I am going to add my constant of integration to that side. And then moving up to this other side, back substituting g minus 27 in for u gives us this implicit solution. We definitely want this solution to be solved for g because of the way this is phrased right here. We want g of t. Right now, g is not a function of t. We just have an equation that relates g and t. We need to solve it for g to have it be g written as a function of t. Now, before I solved for g, what I elected to do was I elected to find out what my constant was. So I put my initial condition in. I put 91 in for the g here. I put 0 in for t. So that just gave me a c on the right-hand side of the equation. And then 91 minus 27, 64. 64 to the 1/3 power. Well, that's really the cube root of 64, which is 4. And then 3 times 4 is 12. So our c value is 12. I didn't really show these steps. I kind of did the concluding steps all at once and pretty much in my head just because I was running out of space on the screen here. But if I put a 12 right here in place of c and I want to get g by itself, I'm going to have to undo this multiplication. So I divided negative t plus 12 by 3. and then I'm going to have to undo this power. So to undo a 1/3 power, I can raise to the third power, right? You undo a cube root with a cube. So I have that fraction being cubed now, and then I just had to undo that minus 27, add the 27 to the other side. There's my function g of t. And then it says, based on this model, what is the internal temperature of the potato at time 3? So if we toss 3 in place of the t, -3 plus 12 is 9. 9 divided by 3 cubed is 27. 27 plus 27 is 54. This would have received full credit. I just decided to simplify it a little bit. So there is the potato problem.